So we have for a long time, and by we I mean like psychology and sort of research fields in general, when we go to create scales, we typically use things like Likert scales, so that people can sort of slide over from disagree to agree on some continuum to indicate the differences in how they agree to that item. But for the most part, you could have asked those same questions as just yes or no, like do you agree or do you not agree? And we can use that would be, we couldn't then use like a multiple regression to predict those items, but we could use instead logistic regression. Let me check real fast. I'm always like paranoid now that I didn't record. I don't think I did. Let's see. Nope, it's recording. Perfect. It's making me paranoid. There was like one time we did a whole thing and I didn't record and had to go back and record the whole thing. All right. So we're used to looking at predictions, like these kinds of graphs that you see on my left here. We're sort of used to seeing, linear predictions, straightforward linear predictions. And the reason we like linear predictions is because the change, no matter where you are in the predictor. So if you imagine, it's not really labeled down here, but if you imagine this is some kind of X. Across the bottom here, it's going to be kind of weird because if I do it too low, it's cut off. This is some kind of predictor going across where, you have, the higher on the predictor you go, and it spreads out from some low to high number, right? We're used to, I'll even draw one on there. We're used to seeing graphs that, sort of have a linear function like that. The reason we like linear functions is because no matter where I am in the predictor, if I go up one unit in the predictor, the change in the outcome is exactly the same. There's a constant change with linear functions. No matter where you are on the scale for the predictor, the change in the outcome is the same. A 1 unit change in X leads to a B, whatever the slope is, change in Y. It doesn't matter where you are. It's the same change. What changes here is that with logistic regression probability, if you're down here at the bottom, right? So if you're somewhere, I'll use a different color. If you're down at the bottom of the scale, somewhere in here, right? Somewhere in there, between those sort of values there, the rate of change, if I go from, from a 1 unit change in that predictor, I'm getting very little change in probability. My chances of actually asking or responding 1, which is, again, success or whatever, my chances of responding that change very little. And it's the same thing up here at the top. If I'm between, these points somewhere on the predictor, my change in probability is very, very small. But if I happen to be somewhere in here, there's almost a linear change, not quite, but in between points in the middle, you get a much faster, rapid change right near the middle. So that's what it says here. The change in Y, in probability units, given X, depends on the value of X. That's not something we've had to deal with before. Before, the change in Y didn't matter where you were in X, it was the same change. If I went from, if this is on the bottom, let's say this is a 10-point scale, if I went from 1 to 2, the change in Y was the same. If I went, as if I went from 9 to 10, or from 4 to 5, or 7 to 8, didn't matter where I was, the change in Y was the same. Now the change in Y matters where you are next. There's a different change, so that in order for us to sort of interpret and understand what the slopes are doing, we have to do a little bit more sort of investigation to figure out, okay, well, how much change in Y is there? Or it depends on where you are in X. So we have to sort of plot out different values in X to see how much change there are depending on where you are on a predictor scale. That makes things a little bit more complicated, which is why we typically start talking about regular linear regression and not jumping into logistic right away. So all of a sudden, and this is why people in general like normal distributions and linear effects, because they're easier to interpret. There's no need to, there's no conditions. It's just like, well, this is the relationship, and it's like that for every aspect of the predictor. It makes things a little bit more it makes it a little easier to interpret, and you don't have to worry about where you are. It's the relationship is the same regardless of where you are in the predictor. All right, so far so good. Questions about that? That's an important sort of aspect here. The rate of change is now dependent on where you are on the predictor. That's unique. That's different. It's very different. This is why this is a departure from the rest of the general linear model, normal distribution stuff. All right, let's move on. Okay, so we're used to the B0. We're thinking of that as A, if you like a regular regression. What we think of as the intercept value. It still is. It's still the intercept value perfectly. I mean, you can interpret it that way. But because the shape of the line, these sort of S-shaped curves, the interpretation of B0 becomes a little bit different. B0 is now what moves the curve from the left or to the right. And B0, again, it's the regression slope, just like it always has been. But the value of the slope is actually given typically right at the inflection point. So where's the inflection point? And what the hell is an inflection point? I mean, you know what an inflection point is? Yeah, it actually pretty much is the middle, right? It's in any graph, the inflection point, and this is true actually of normal distributions or anything. If you think about a normal distribution, you got the bell-shaped curve, right? At some point, this graph is going up, and at some point it sort of switches to sort of curving back this way. So it's going this way and then curving the other way. So at some point, which there's a mathematical way to figure it out. At some point in there's an inflection point, and there happens to be one here as well, right? So there's two inflection points in a normal distribution. And it's interesting, this is just a side note, it has nothing to do with logistic regression, but if you were to draw a line down where those inflection points are on the graph, that would be your -1 and +1 standard deviations. They usually fall right at those inflection points around the mean. So you have the mean in the middle, and then your +1 and -1 standard deviations are right where the inflection points are on the normal distribution. I remember that not because it's something of mathematical importance to me, but whenever I'm drawing out a normal distribution and I want to place, where 1 and where -1 and 1 standard deviations are around the mean, I usually try, to draw it wherever that is, so it sort of makes sense, so that the area sort of works. The percentages you get for like a z-square distribution sort of work out, and they actually fit in the graph pretty well. So that same idea goes here. This line is sort of going upwards, at some point in the middle someplace. Usually it's right wherever the line passes the 0.5 mark, there's an inflection point. The inflection point is more important here relative to these inflection points. The inflection point here is where your probability, as you go up in x, the probability starts to shift from being more likely to say no or to be in the 0 category to all of a sudden switching at that point to being more likely to be in the yes category. That's usually the sort of cutoff point of sort of placing people into, the yes or no or male, female, or whatever the dichotomy is. It's what's sort of placing them into those categories. So that's the inflection point there. How do we know what value falls at the inflection point? The threshold value, or probability of success, equals sort of 0.5. If I actually take negative of the intercept, this value, and over the slope value, this is only if there's like one predictor, and you sort of divide those, you can actually get a threshold value, which tells you what is the x value that corresponds to exactly 0.5%, 0.5 probability of sort of answering yes. So that's what that negative B0, B1 is. If you're interested at all in sort of measurement theory and testing and stuff like that, the B0 and B1 have different interpretations, which I actually like because they sort of help things make some sense. The B0 value, because it moves the curve, go this way, go back a second. If you think about this curve and moving the curve either up or down, what does that actually do? So if this curve moves this way, that means that the item is more difficult. The reason why is I have to have more of the predictor. I have to have more of whatever this is to get a yes on this question, or 1. This comes out of testing, so think about pass-fail. You have items on a test. If the item is difficult, let's say this is a test on the recent midterm. A more difficult question means that you have to have more 524 knowledge to get to a higher probability of getting that answer correct. That's a more difficult question. If this question goes this way, it's an easier question. You can actually have very little 524 knowledge and still have a pretty decent chance of actually getting it correct, a decent probability. So that the B0 is often thought of as the difficulty in sort of testing. This is the item's difficulty. Okay. Difficulty. Okay. And regression, as the regression slope, how steep or shallow that slope is. We used to think of that, all right, so the higher the slope is, the more that predictor is related to the outcome. All right, so that there's a stronger relationship between the outcome and that predictor. That's still true here. If I were to take that same line, if this line were more flat like this, that would mean that the relationship between the predictor and the outcome is actually not very strong. The steeper this goes, the more related the item is to the outcome. But in testing terms, we tend to think of this as, it's often known as the discrimination. Okay. So again, if you think about this as a testing item, a steeper slope means you can actually, I can in a small area, right? I can tell the difference between people, say, I don't know, I'm just making up some lines here. These people, I can discriminate against people in this range, meaning that someone who is just a little bit high here, I can tell actually have more knowledge or more capable of answering this question correctly than someone who has lower than this, right, in this small area. If it's steeper, I can actually discriminate a more narrow range of people. It's more discriminating. If it's flatter, I have to go a lot farther along the predictor to actually then be able to tell people apart. So it's less discriminating. So the discrimination is actually the term they use here. And I know the discrimination tends to have a sort of negative connotation, but it means in the purest form of the word, which means to actually tell things apart, to actually be able to discriminate one thing from another. Discrimination just means to be able to separate things out as being alike and different. So in that sense, a more discriminating item does a better job at telling people apart, telling people who have high versus low probability of getting an answer correct if it's a testing. In psychology, it gets a little bit weirder. Like if this is a depression scale or something like that, and we're trying to figure out a difficult item means you have to have more. You have to have more of a more depression in order to answer a certain item correctly. It's weird to call it a difficulty, so it seems a little strange. And again, discrimination does still work in terms of being able to tell people with high and low depression in a very sort of narrow scale is actually still beneficial. The item actually is more related to the outcome, to depression, to the thing we're trying to predict, and therefore is more discriminating. So those words still work, but this thing is still typically thought of as the sort of threshold value, where the best sort of discrimination occurs because you're actually shifting from being your probability being below 0.5 to being above 0.5. All right, questions about that stuff? I'll give you a little sort of background of how you might actually in logistic regression have see people talk about the discrimination of the item and that kind of stuff, and it's just really talking about the slope. And the intercept is oftentimes referred to as the difficulty of the item. Anyway, so this is just showing that if I actually if I hold the the intercept constant at -0.4, or sorry, -4, but I change the slopes, sort of what happens. This one's sort of off screen a little bit. This one has a higher slope. This one's slope is sort of lower. And this one's slope's even lower. So as the slope value sort of goes, if you're shifting the slopes around, this one's the sort of bottom one, has the lowest slope. This one's the sort of middle one that has the sort of middle of the road slope, and this one has the highest slope, which is the one in green. So in that sense, the intercept values, the difficulty is the same for all these items, but we're changing the discrimination, changing the slope value. Here you have three different items that have exactly the same slope, but differ in their difficulty. All right, so which item is the most difficult? Yeah, so the reason why, so think about that 30 to 100 thing on the bottom. Think about that predictor being, Psy524 knowledge, and on the side here, right, is your likelihood or probability of answering a single test item correctly. So the red item, right? So think about where 0.5 is. So here's 0.5. I can get by with having 60 points of Psy524 knowledge, whatever the hell that is, right? I can actually get a 0.5 with just having 60 of whatever that predictor is. For the green item, I actually have to have more knowledge, because what's 0.5? 0.5 is somewhere like here. I have to have 20 more units of whatever this predictor is to get to the same probability of answering this question correctly. So it's a much more difficult item. I have to have more of the predictor to get to the same probability that this item has with less of the predictor. So this is an easier item. This item is more difficult. And this item is really difficult because, look, I can have 100% or whatever the hell this is of Psy524 knowledge, and it's still not guaranteed to answer this question. I still only have less than a 0.5 chance of answering this question correctly because it's a really difficult item. So even people really high on the predictor aren't guaranteed to answer this question correctly. But it's actually really difficult. Okay? So again, this whole thing deals with this idea of a logit, which drives people a little nuts. But all this stuff is just, it's the same stuff being displayed in different ways, and hopefully you sort of can grasp onto one of the ways, and then that'd be good. So if we're trying to predict probability, so the way you read this is the probability that y will equal 1, because remember y is just a 0 and 1. The probability that y will equal 1 given some x, some predictor, over 1 minus that same thing. This is the odds ratio we were talking about before, p over q. We can display that as, look, this is we use pi to, we oftentimes will use Greek letters to represent parameters, population parameters. Well, pi oftentimes is used to represent, population probability. So this is pi over 1 minus pi will equal to the exponent of this is sort of the anti-log of whatever those values we found when we actually did the logistic regression. If we then take the odds ratios are sort of even they're sort of strange. I know logits are sort of weird. They're these sort of standardized sort of values that are sort of hard to gauge what they really mean. But odds ratios are a little easier to understand, but they're still sort of strange for us. It's usually, again, seen as the probability over 1 minus probability. Less than 1 equals less than 0.5. So 1 in odds ratios equals 0.5 probability. So as you go above 1, that means your probability is actually going closer. You're actually more likely to answer yes. As you go below 1, you're actually less likely. And in terms of logits, positive logit values will equal values in the odds ratio that are above 1. And negative logits will correspond to odds ratios that are below 1, but it never goes negative. Like odds ratios are always, just like probabilities, are always positive. There's no negative probabilities, no negative odds ratios. Okay, so greater than 1 means that you have a greater than 0.5 probability of answering that item correctly or affirmatively or getting a success, whatever the term you want to use. If it's below 1, it means you have a less than 0.5 probability. So if we actually then take everything to finally taking the natural log of both sides, we can write the equation in terms of logits. So this is what we want to get to, because this, forget about all this other junk. Forget about this for a second, right? This is familiar. This is going back to our roots. This is like, okay, this is regression. This is literally a simple single predictor regression. This is your y equals mx plus b, right? This is like high school level regression, maybe even junior high school level regression. When you're starting plotting lines and trying to do rise over run. This is it. You got an intercept plus a slope times your predictor. This is simple. It's nice. It's neat. It's tidy. The only thing that's different is to be able to do this, we had to do this sort of transformation. The transformation is not difficult, it's just weird. Let's take probability and convert it over to this odds ratio thing, and then take the natural log of that to get to this weird logit thing. All that stuff doesn't matter. All that does matter is that logits are linear and they're continuously scored, which is why we can take our regular old regression and predict it with it. And it becomes simple. I have a nice simple regression. I'm just predicting this weird outcome, this weird transformed outcome, but it's not any weirder than saying, oh, I have two groups that are different on this square root transformed outcome that I did because I had my data was skewed. So the significant difference in square root of reaction time, or the log of reaction time, those are also strange. Those are weird metrics, but we do that all the time just to try to fix the fact that our distributions aren't normally distributed, or they're skewed, or whatever it is. This is doing the same thing. We know probabilities have this S-shaped function. This process sort of transforms it into something we can use. So we do that, and then we predict it with our regular old regression, which is why, like, for the most part, 90%. And I'm making that number up completely, of logistic regression and regular multiple regression are pretty much the same thing. They do the same things. Everything's sort of the same. The goals are the same. The points are the same. It's just how we get to being able to use this regular regression equation in logistic regression takes a couple of steps, and it can be kind of odd, and we have to interpret the outcomes a little differently because they're not going to be consistent all the way across the X predictor. All right, and we can do this for multiple predictors. This is the natural log of the probability over 1 minus probability. This is our logit score for y, and we just have multiple predictors. We can interpret multiple slopes or same one intercept. The only thing that's different is our outcome is sort of weird. So log odds are like linear function, or a linear function of the predictors. So when I'm saying log odds, that's logit, right? So the log of the odds ratio. Log odds and logit mean the same thing. The regression coefficients go back to their old interpretation. So as long as we're talking about the logit units, and when things are transformed over, we can actually interpret the intercept and slope the same way. All right, well, if whatever our slope, whatever our intercept is, that's the value of the logit when all our x's are 0. The slopes are, anytime you have a 1 unit change in x, that corresponds to a slope, a b amount of change in the logit version of y. Those things all correspond, and the change in y is consistent on all levels of y as long as it's in the logit form. So we get a nice linear function. Remember, we've gone from this, we've taken this S-shaped thing that is scored from 0 to 1, right? And we transform that over to, it doesn't matter, to this new thing. So these scores on the bottom stay the same. This is whatever x is, it's still the same. Here's x again. It's just we've now stretched this 0 to 1 out to being sort of positive to negative infinity over here. It's now been stretched out, this linear function to this continuous function, and this S-shaped curve has now been stretched out to being a linear curve, where this is the logit and this is the probability. Right, so all this has done is sort of transformed the probabilities into logits, and we're doing all the work on the logit version because it's linear and it fits all the requirements of regression. And we can actually test for significance. We can test for the significance of the model and the significance of each predictor and all in the logit without it doing anything. The complication is all done on the computer. It doesn't matter. We can do all this stuff. It'll tell us if it's significant or not. The problem comes down when you actually have to interpret what, you're getting a slope value. So the slope for x1, how we interpret this thing is being given to us in the logit form, right? As x changes 1 unit, y changes whatever b1 is in logits. What the hell is, what does that even mean? It's sort of hard to interpret. So the confusion about this stuff is that in order to interpret what this actually means, we have to do some kind of conversion to be able to talk about how this change corresponds to a change in probability. That's the part that sort of, makes it, a little complicated. That's the extra bit that complicates things outside of the multiple regression approach that we're sort of more used to. All right. So the big picture, convert the logit, we predict the logit, we do our testing, like model testing, all of our coefficients, all those things all get tested in the logit. And the only difficult thing comes in when we actually have to figure out, okay, well, how much change in probability actually corresponds to these slopes and stuff, that we have to sort of figure out a way to interpret that. And because we know the probability is different at different levels of the predictor, that becomes a little interesting. Okay, so let's talk about an example. Examples are always good. This is from the textbook. So if you want to sort of revisit this in the textbook, you can sort of get a different sort of take on it and stuff. So this is I don't know. Tabashkin and Fidel seem to be obsessed with two things: belly dancing and skiing. Seem to be two of their big favorite things to talk about. So at least there's no belly dancers, administrators, and politicians in this one, which they tend to like to use in their examples. This one's just, you're going to go skiing. You have a bunch of people going skiing. This was just like, 2, 4, 6, 8, 10, 12, 14, 15 people are, they go skiing. And the predictors are two different things. You have the difficulty of the run, of the slope, right? 1 being sort of easy, to 3 being difficult. And even though it's only 3 scores, we're going to treat that continuously. All right, so we're going to treat it like it's interval. That the difference between difficulty between 1 and 2 is the same as between 2 and 3. It's not really enough choices to be truly interval, to be truly continuous, but we're going to pretend that it is, and we're going to use it as a continuous predictor. The other one you have in here as a predictor is the season, where 1 is autumn, 2 is winter, 3 is spring. I'm going to assume that winter is probably the best time to ski. Autumn and spring both seem bad. I mean, I guess you get an early snow in autumn. Maybe that's good. But it seems like spring would actually be like icy and probably mostly man-made or something. I don't know. So I think the idea is that winter is probably the best time to ski. Autumn and spring are sort of subpar. But depending on when you're skiing, does it actually affect your likelihood you're going to fall while skiing? So that's what the outcome is. Person went skiing, did they fall or not? Right, seems pretty simple. So we want to be able to take the combination of the difficulty of the slope and the season to be able to put together a prediction of whether a person would fall while skiing or not based on those two predictors. And you can see where this would come up where, if we actually track these 15, or let's say it's 1,500 or some very large amount of people who actually did or didn't fall while skiing under these conditions, we might be able to predict or at least warn folks, hey, if you're skiing under these combinations, you're likely to falling as much higher or getting hurt as much higher. Maybe making decisions about whether or not to close the slopes or the runs or something based on these sort of combinations could be very useful in terms of predicting whether or not someone would fall and potentially get injured while skiing. All right. So season is a discrete predictor, so it's just 3 choices, even though difficulty is also 3 choices. Season isn't even ordinal. It's not like there's more or less season across those 3, so it's just a categorical variable. The numbers are there just to sort of separate them out. So we're going to do something, because there's 3 of them, we actually have to break up the 3 different groups into 2 different two-group comparisons. So this is typical of, we did multiple regression as well. Anytime you have more than two groups, you got to cut those groups up into smaller two-group comparisons in order to put them into a regression equation. This is the same. What's different here is that when we did this in 485, we used contrast codes. So contrast codes, contrast codes are sort of synonymous with like ANOVA. So we use sort of ones and negative ones, and they typically sum to they'll sum to 0, and you have to cross multiply to get them to be orthogonal, all that stuff. These are contrast codes, and we did this in 485 using all the like 2, -1, -1, and 0, 1, -1. All those codes we did are contrast codes. They're contrasting the groups to one another with the idea of keeping the mean, the actual comparison at the mean between the groups, which is why there's a 0 somewhere in here that both these groups are being compared to, which makes it like ANOVA. Comparing two groups to the average, which is what ANOVA does, compares groups to the grand mean. Instead, this is actually using a different approach, which is strangely, and I don't know why, it's called dummy coding. So dummy coding is more like t-tests. We're taking and comparing groups directly to each other, right? So instead of taking two groups, comparing it to a mean, I want to compare one group directly to another, compare their means directly, just like we do with the t-test, okay? So these just use zeros and ones. They do not sum, they don't have to sum to 0 like contrast codes do, but the only way to really figure out with contrast codes, what's being compared in each contrast just by looking at the contrast by itself. With dummy codes, you don't. You have to look at the codes holistically, all together, to figure out what groups are being compared to one another. So it's not like with contrast codes, if I have three groups and I'm doing 2, -1, -1, well, I know I'm comparing group 1 to groups 2 and 3 combined. I sure wrote that in a bad place. 2, -1, -1. I know I'm comparing group 1 to these two groups sort of combined. With dummy codes, I can't just look at one of those codes by itself and be able to know that. I have to look at them sort of combined. So what we're going to do is season 1 is coded 1. So we're going to create two predictors. One's going to be called season 1, and that's going to be coded. So remember, we have 3 groups. I forget the order. It's autumn, winter, spring. Autumn, winter, spring. So this is going to be 1 for autumn and 0, 0. So this is, remember, autumn, winter, spring. So right now it looks like, okay, well, I'm comparing autumn to those two combined. Sort of. It's not quite right. This looks like this, right? 2, -1, -1, 1, 0, 0. It's actually not what's being compared. I'm not just doing autumn versus winter and spring. So I have to look at the season 2 predictor that we're making, which is now is coded 1 if winter and 0 otherwise. So now it's going to be 0, 1, 0. So those are my two codes. So what this does, and it seems sort of strange, is to create a scenario where we're gonna try to figure out the intercept value is going to be equal to whatever group is all zeros. So what group is all zeros? What do I mean by that? It sort of says stuff in here, but say it again. Yeah, so spring is, we're actually, by doing this, by putting spring at 0 and 0, I've now effectively said, all right, whatever my intercept value is, that intercept value is the value for spring. Right? This one says this is basically autumn versus spring. And season 2 is winter versus spring. So both of these comparisons are comparing one of the seasons to spring. We've actually designated that this is our like control group or comparison group, whatever word you want to use. This is the sort of the comparison group that we want to actually, that we've identified, and we're comparing both the autumn skiing to spring and winter skiing to spring. We're using spring as our control. I know that because spring has got both zeros. Whatever slope we get for this one, the slope for season 1 is going to tell me how far autumn is away from the intercept, which is spring. And B2 is going to tell me how far winter is away or different from the intercept, which is spring. Okay, so that's why it's coded this way. We're comparing all the groups directly to one another. It just happens to be we're designating the spring season as our sort of comparison, and everything's being compared to spring. So we can see that sort of here. It's sort of you have to sort of compare that. Well, so here's season. So in season 1, this one's coded 1. This is coded 0. That's coded 0. Right. The only place where you see the codes of 0, 0 is when they're actually in the spring season. So this person is part of the sort of comparison or control group. So is this person, right? So is that person. And that's because, remember, the intercept is the value of y whenever x is 0. Well, when are these x's 0? They're 0 when both of them are 0 like that, which means you're in the spring category. So the intercept now is fixed at whatever the value for spring is. And each of the other slopes, like season 1, season 2, are actually going to tell you how far each of these groups are from spring. It's comparing it, saying how much has it changed away from the intercept. Okay, questions about that? That was a quick rundown of dummy coding, but all right, moving on. So we've now separated the seasons into 2 different predictors. They're now 2 group predictors, so we can actually get differences between those, and the slopes are actually now sort of more interpretable. Again, we left difficulty alone and treating it as continuous, so we can go forward. So here's the good news. We're going to use the magic of computers to really solve for a lot of the difficult parts of this. We're not going to go into how do we actually solve for the slopes or intercept values, because it's actually, it's mathematically advanced. So we've got everything into logistic regression, transfer everything into a logit, and at that point we then predict it. It's more or less multiple regression. But we typically use things like maximum likelihood and other things to actually get those values, especially the standard errors for each of those, because they're not calculated in the same way as they are for regular multiple regression, because we're dealing with this logit transformation stuff. So we're not going to get into this in an applied course. There used to be a course in our department that taught this kind of stuff. It was it's like Psy524. We haven't taught that in quite some time. But there's lots of sources you can go to if you're interested in how this actually happens. If you're interested in the mathematics part of it, I recommend seek it out. But I'm not going to cover it here. I'm not going to expect you to solve in a logistic regression, solve for the slope and the intercept values, because 1, we don't have time to go into that, and 2, it's not really relevant to a course that's on sort of the applied aspect of this stuff. So we're going to generate, we want some y predicted value, and our y predicted value is going to be what we want. It is in means that probability is going to be that exponent value, the e value, raised to our our prediction equation with our intercept. This is like our b0, our difficulty, our season 1 and our season 2 predictors, all trying to predict whether or not they're going to fall. And then we're going to have that over 1 plus that same value to get it to probability. All right. And then we can actually go through and test each coefficient, like the B1, B2, B3, with something called a walled test, which is, it's like it takes that slope value over the standard error for that slope. They don't quite, because it's a different animal, like it's not quite linear, the coefficients, the walled values aren't, if I remember correctly, they're not like z's or t values. They're more like chi-squared values when you go to test them for significance. You don't look them up in the same way. But in SPSS, it will give you the walled test. It'll also then generate the probability for that test too. But they're generally not, you take the slope divided by the standard error for that, and you're getting something closer to, I think, if I remember correctly, a chi-square instead of a z or t test. So, through the magic of computers, we put that model in there with our 2 seasons, our difficulty, all predicting our chance of, whether or not someone fell or didn't fall. So we put that all in here and we get back, here are our coefficients, here are the standard errors, and here are these sort of walled values that you get for each of these coefficients. So you probably noticed I skipped over, typically in multi-regression, you look at collectively, did all the coefficients predict the outcome, and look at that as sort of like an ANOVA test. I sort of skipped that. I'll come back to that in a second, because it's not an ANOVA like it usually is. We're going to be doing a log likelihood difference test. But when you actually generate the coefficients, you do get tests for each coefficient the same way you would in a coefficients table with a multiple regression. It's just now, how do we interpret these things? So you see the negative 1.776, 1.01, 0.927, negative 0.418. How do I interpret those values? Think about this. Yeah, think about like so we have difficulty, and forget about season, but season 1 and season 2 are 2 predictors. So, who does it actually apply to? Who actually score that? Who would actually get a negative 1.776? Of these folks, is anybody listed here going to be predicted to have that score? Not the ones, all the zeros. So it's a good start to think, all right, so this person might possibly have that, because there are 0 at season 1, 0 at season 2. But the way that this gets interpreted, right, is this is the value for y when all the x's are 0. All right, for season 1 and season 2, we set it up so that we have 0, and that's our sort of comparison group. But difficulty is sort of problematic, because we don't have a 0 difficulty. So that negative 1.776, it's a sort of projected value. So if you're skiing, so who skis 0, 0? That was the autumn folks, I think. Right, so people in autumn, not autumn, spring. Spring was the comparison group. So if you're skiing in spring, and you're skiing on a difficulty level that is even easier than easy, because you got to think it's got to be, what would 0 be? Or if 3 is the most difficult and 1 is the easiest, 0 is going to be easier than easy. It doesn't actually exist here, so it's really an extrapolation to a point that doesn't really exist on the predictor. So it's sort of a weird prediction, but we do it all the time with regression, because we'll put in predictors that don't have zeros, and then it actually then has to project what it would be like if we had a 0. So this is basically the value for someone skiing in spring on a difficulty level slope that's easier than the easiest slope. All right, so that's already strange, but that's sort of how it works. But what does that number actually do? This is the value for what? Maybe let's go here. So if I go up in difficulty, right, each unit as I go up in difficulty, what's actually changing here? Yeah, so if I go from 1 to 2 difficulty, I should go up 1.01 what? What is the y? That's exactly the question. What's the y we're talking about here? Is it just 1s and 0s? It's not the probability either. It's close, closer. Say it again. It's not, because how would you interpret that? The 1.01, you know, so if difficulty goes up 1, I increase 1.01 what? What is the units that are increasing here? Logits. That's exactly right. I love the way you said that. That was great. It was like exasperation. Logits. Yes, so as you go up in difficulty, right, if I go from an easy slope to a to a medium slope, moderate slope, the logit value in y, the logit form of y, will increase 1.01 units. Okay. If I go from, remember, season 1 was winter, I think. I forget what I said now. Season 1 is coded 1 for autumn. Nope. So it's autumn. So if I'm skiing in autumn, right? I'm actually going to go increase 0.927 units. My chance of falling, my logit version of falling, is going to go up 0.927 units away from this negative 1.776, which is our spring skiing, right? So it's going to increase. If we're skiing in fall and autumn, our chance of falling is going to go up 0.927 logit units. However, if I'm skiing in the winter, it's going to go down. I'm going to reduce my chances of falling by negative 418 units. The reason why these are important, again, it's completely impossible to interpret what that means. What does it mean that difficulty increases my logit version of y 1.01 units? It's sort of hard to tell. It's not really, we don't really use these values to interpret anything. What we do use these for is I can take the coefficients, I can generate standard errors, and I can tell which of these are actually significant, which, as you can probably guess, none of them are. None of these are significant predictors. Okay? And if I want to know, the one thing about logistic regression that makes it sort of difficult or tricky is that I can't just interpret the change in these things sort of alone. I need to look at them sort of holistically. So I can actually plot this out where I have, if I want to know the actual probability, I got to plug these values into this equation. So I'm going to start off with negative 1.776 plus 1.01 times the difficulty plus 0.927 times the season 1 minus 0.48 times season 2. Whatever that value is on the top, I'm going to divide that by 1 plus the same value, and then it'll give me the probability. So you can actually predict what the probability is for any single combination of those things, but usually we think about these things as change, like how much change we'd expect in the outcome with a 1 unit change in the predictor. But to do that, we can't just do it. Like we can't just interpret these, like I can't just convert the single number to a probability and say, well, that's how much the probability changes for a 1 unit change in difficulty. I actually have to plug it into this equation, vary whatever it is I want to vary between, say, difficulties from 1 to 2 to 2 to 3, and see how the probability changes inside this whole equation, which is why I'm saying the interpretation gets a little harder. And that's because depending on where you are on difficulty, depending on where you are in season 1 and season 2 are not so difficult in terms of there's really just one change. It just goes from 0 to 1. But difficulty actually has, 1, 2, and 3. The change in probability going from 1 to 2 may be different than it is going from 2 to 3 because of that S-shaped curve, right? So anytime you have an S-shaped curve, depending on where you're on the predictor, your probability is going to change a different amount. So we actually have to sort of plug all that in and look at differences across things. And I never really had a good explanation for how to look at that until I sort of, working on a project a couple of years ago, I sort of figured out a way to do it, which now I think back it seems like simple, but I had never seen anybody do it before. And we'll go through that some, I think, in the lab. I'll show you sort of how to take, these kinds of values and actually turn it into probabilities and then see what the changes are like in, say, going from one difficulty to another and that kind of stuff and actually look at those. We'll do that in lab. Okay, so how do we interpret coefficients? The tests of the coefficients are approximate chi-squares, so they're tested as chi-squares. And none of these coefficients are significant. So all these are all sort of, 1 degree of freedom sort of, I think, tests for sort of chi-square, the critical values. These aren't going to pass that at all. I think chi-square is 3 point something for a 1 unit, 1 degree of freedom test. The coefficients are placed into the model like in a regular multiple regression in order to predict individuals' probability. It's just that you're doing so and then raising e to that number and then dividing by 1 plus that number to get the probability. So it's a little extra steps to actually figure out what the predicted probability would be. You can't just, plug in numbers like we used to and sort of just, solve for that thing. We actually have to put it into this equation to figure out the actual probability. Because by themselves, they're just telling you how much the logit value is changing. If you want to know how probability is changing, you actually have to plug it in here. All right. So questions about this stuff? Yeah, so this is how, so like for difficulty, if, remember you're starting off at a difficulty of 0, which doesn't exist. So the constant is assuming there's a difficulty 0, which is why the number, which is how we get this number. So it's sort of assuming a fictional difficulty, right? But as you change difficulties, going from 1 to 2 or 2 to 3, this predicts that you would go up in 1.01 logit units. Right? So let's think about this for a second. Right? Think about, so we have this negative 1.776 plus, right? 1.010 times a difficulty. So let's say someone's skiing on an easy ski run, right, in winter. All right, so go back to your second. Someone who's skiing on an easy ski run. So easy ski run, nope, they're skiing in autumn. They're skiing in spring. Easy, oh, okay, here's someone. This person's skiing easy run, and they're not skiing in autumn, they're skiing in winter, right? Because this is the season 2 says is the winter code. So I'm skiing in winter, right? Which means I want 1 point, it's the difficulty of 1. So if someone's skiing in winter, I'm going to go forward a little bit more. It means that it's going to be 0.927 times 0, because they don't have, their code for the first season is 0, minus 0.418 times the winter, which is going to be 1. That. What's that equal to? This looks just like a regular regression equation, right? We're just plugging in the slopes times whatever value they have. This is the value for difficulty. This is season 1. This is season 2. All we're doing is plugging in, what someone's score is for those. And what do we get? So let's just say I wanted to figure out what's the probability for this person right here. I want to know what's the likelihood that this person is what's our probability for falling for this person based on our equation. So I'm going to plug in for difficulty, their score is 1. Again, skip season 2, because season 2 we broke up into season by itself. We broke up into these 2 dichotomies, so I need to know to plug in their season 1 and season 2 scores. So those are my 3 values. My difficulty of 1, season 1 is 0, season 2 is 1. So this is a person skiing an easy ski run in winter, negative 1.184. And we confirm that number. Okay, so remember what we just solved for, right? It's just this part piece of this equation up here. So how do I get it to be probability? Well, I need to take e raised to negative 1.184, right? And divide that by 1 plus e raised to negative 1.184, and that's going to give me the probability. So for that, we take (1.184), and I'm going to take e to x, raise it to that. So that ends up being 3.267 is what this equals to, right? So if I divide that by 4.267, that should give me my probability. 3.267 divided by 4.267. Oops, crap. 3.267. 3.267 divided by 4.267. I get 0.766. Oops, can't read that. Equals 0.766. Anybody else get that number? Did I screw something up? Okay. So someone who's skiing an easy ski run in winter has about a 0.766 probability of falling. Okay? So that's great. That's a good prediction. We're able to predict the probability for that person, but we need if we want to know like what the change and stuff does, like changing from one season to another. Let's say I'm interested in knowing, all right, well, how much more likely am I to fall in spring relative to winter? I'd actually have to figure that out by, so I'd have to modify this equation a little bit. So if I want to go instead of someone who is, so we have to keep everything else the same. So difficulty still stays at 1. And now for the season 1 and season 2, someone who skis in spring should have a 0 for both of these. Right? That's what we said before, that if you're skiing in spring, right, so spring was 3. So if you're skiing in spring, you should have a 0 for season 1 and a 0 for season 2. So I can actually figure out. So I'm going to put, so for, this was easy winter, so probability was 0.766, right? So let's actually readjust some of this to say, all right, what would this number be if it's now 0 for both of those? So it's really going to be negative 1.706 plus 1.010 times 1, so it's just plus that, and that's it. So it's 1.776 plus 1.010. Like that. Okay. So then we take, I'm going to plug that in here. Negative 0.766, negative 0.766. So what do I get if I take e raised to negative 0.766? Oh, I think I just screwed up the last time. Wait a second. I think I screwed up. Hold on. I think I realized what I did. So before, what was the number before? 1.08 something? That's the only problem with the light board. There's no like Control Z or whatever. There's no undo. What was the number that I had here before? E raised. Say again. 1.184. 1.184. I forgot the negative. I went e raised to 1.184, which is a very different number. So hold on one second. 1.184 negative e raised to that is a very different number. So this number was not 3, whatever it was. It's actually, this actually should be 0.306 over 1.306. 1.306. So going back to our original equation for a second, this should again be negative 1.84, which means easy winter, that you actually should have a pretty low probability of falling. So what's 0.306 divided by 1.306? You actually, this makes more sense. You only have a 23% chance. So this really should be 0.234. You have a pretty low chance of falling. 0.234. All right, this is for our easy winter skiing. That should be our least likely chance for falling. Now, let's go back and do this. So this is now our easy but spring, right, 0, 0, of negative 0.766. And I need to go through and replace this stuff. So negative 0.766. These will all change. So these. So that. So if I'm now I want easy spring. So that's negative 0.766 and negative 0.766. 0.766 negative, erase that number. This is 0.465, and then 1.465, 5, not 4. So 0.465 divided by 1.465 equals 0.317. So 0.317. So if you look at this, the change, so we held difficulty the same. The change between winter and spring is 0.317. Crap. 0.317 minus 0.234 equals, it's only about, so if I'm skiing in spring, I'm now going to be 8% more likely to fall than if I ski in winter, assuming that they're both easy slips, right? I'm on easy slopes both times. We're out of time, but if we were to do the same thing for, to actually figure out easy autumn, right? We can do the same process and actually calculate what it would be like for easy autumn. And you'll see that the change between like winter and autumn, or sorry, I should say the change between autumn and spring, because remember spring is our, this is our comparison group. It's not going to be 0.083. So just because the change of probability between spring and winter was 0.08 doesn't mean that autumn will actually have the same change, which is sort of odd when we think about it, because we're used to, again, with linear trend, linear stuff, that any change between values, predictors, should remain sort of the same. But we'll see it's not going to be, obviously, because the weight here is different than it is there. So depending on which one gets the 1, it's going to change somewhat. But we can actually figure out, changing from one to the other, what the actual change in percentage would be. And we can do the same thing. We can say, all right, let's hold everything constant. We'll look at everybody at winter and see, okay, what's the likelihood of, if I go from an easy slope to a medium slope, what's the change in probability? If I go from medium slope to a difficult slope, what's the change in probability? And we can figure out what those changes would look like, and they're not going to be the same. They're not going to be consistent because it's not a linear function. They're gonna change depending on what change you're talking about, going from easy to medium or from medium to difficulty, from medium from difficult. It's going to be a different sort of step. Anyway, I'll stop there, and I'll show you how to do this somewhat with our lab assignment, and we'll use Excel to sort of play around with some of this stuff.